Welcome to ECE 320, Electronics 1, lecture number 22, MOSFETs. Now, what we've looked at before are different types of semiconductor devices. If I just have a type of p-type material or n-type material, that can be a light sensor, temperature sensor, things like that. If I take a p-type and n-type, put it together, I get a p-n junction. That's a diode. That allows current to flow one way but not another. Put three devices or three parts together, NPN or PNP, that's a transistor. This is another type of transistor called a MOSFET. It's built slightly different than the other transistors. With a MOSFET, I have a p-type substrate and two N-wells. That prevents any current flow from the drain to the source because there's a reverse bias diode in here. If I apply a voltage at the gate, then what happens is that those plus charges attract minus charges to the surface. Those minus charges produce an N-type, an N-channel, that allows current to flow. So this is called an N-channel MOSFET. As the voltage goes up, I get a bigger channel, less resistance. So for a transistor, transistor is a current-controlled current device. A MOSFET is a voltage-controlled resistor. There's another mode for MOSFET. If I try to push too much current drain to source, I run out of charge carriers. In that case, I'm current limited. If I apply more voltage at the gate, I get more charge carriers, allow more current. That'd be a second use for MOSFETs. It's a voltage-controlled current source. So again, MOSFETs have three modes of operation, like a transistor. They're off, they can be resistors, or they can be current sources. And for the resistance, if I divide by VDS, I over V is admittance. The admittance is related to the voltage at the gate. Now, MOSFETs are rather important. They're what allow things like quadcopters, electric cars to work. If you go to DigiKey and search for MOSFETs, they have 91,000 in stock. If I limit it to N-channel MOSFETs, again, there's like two types of MOSFETs, N-channel and P-channel. The N-channel MOSFET is what we looked at. Flip the P as an N, you get a P-channel. It's like a transistor. Transistors have NPNs and PNP. NPN transistors are used as switches on the low side. PNP transistors used on the high side. The real advantage of MOSFETs are their current capabilities. This is the current that a MOSFET can take. They've got really tiny ones. That's used for things like cell phones and computers. If you don't need a lot of current capability, a small MOSFET will have a much smaller capacitance, much quicker switching time. At the other extreme, you can buy MOSFETs capable of 1,900 amps. That's something you don't get with BJTs. To get a quadcopter to work, or a three-phase AC synchronous motor used in electric vehicles, I need two things. I need electronics, which is capable of high currents. That's what MOSFETs do for you. The second thing you need is microprocessor. For an AC synchronous motor, the voltage that you apply has to be a sine wave that goes in sync with the motor. If the sine wave is in sync with the motor, you're coasting. If it's slightly ahead in phase, you're accelerating. Slightly behind in phase, you're decelerating. Frequency is speed, angle is torque. You need a processor that's fast enough I can sit there and watch where the wheel is in real time and output the correct sine wave. Processors are now fast enough to do that. Connect the two together, microprocessors plus a MOSFET capable of, in this case, 1,900 amps. I can now start building quadcopters, electric vehicles. That's why these came on the market only about 10 years ago. They're kind of nice. MOSFETs are a little bit different than resistors. The resistance, when it turns on, if I use MOSFET as a switch, this is what I care about. For a transistor, the voltage drop is about 0.2 volts when the transistor's on. MOSFETs can be really small. This is 0.4 milliohms at 150 amps at 10 volts. This is just a big hog and switch. I have almost no resistance at huge current flows. The reason we don't use MOSFETs, in industry use MOSFETs, in lab we don't. The reason being is this gate right here, that's the little capacitor. There's a small insulator between the two. If I apply too much voltage gate to substrate, I discharge across that insulator and I burn out the MOSFET. MOSFETs are susceptible to static electricity, so they don't survive our labs very well at NDSU. In industry, where you have more static protection, MOSFETs are really what you use. We use BJTs just because they survive our labs. Really, in industry, you want to use MOSFETs. They're smaller, cheaper, more powerful, quicker, but static sensitive. So going back to MOSFETs. MOSFET has 3 modes of operation. So again, this is like a transistor. If I have a circuit, it's a little bit annoying. I've got to figure out which mode it's in. If it's off, that's easy. If there's not enough gate voltage, if there's a thing called the turn-on voltage. If the gate to source voltage is less than the turn-on voltage, there is no channel. If there's no channel, there's no current. The ohmic region is as I first start turning on the MOSFET, I start getting a resistor. The channel gets bigger and bigger. The bigger the channel, the less the resistance. This is if the gate voltage is bigger than threshold voltage, so there's a channel, but less than, there's a VDS plus V turn on. If I go beyond that, I run out of current. If I try to push the current flow, make VGS is too large, or VDS is too small, then I run out of charge carriers, and I go into the ohmic region, or the saturated region, which is current limited. There's a parameter, K sub n. That's like beta for a transistor, or HFE. This is a parameter of the MOSFET that determines what the current is, either in the ohmic or saturated region. For example, suppose I had your transconductance gain, K sub n, is 250 microamps per volt squared. That's just kind of like beta. If the turn-on voltage is 1 volt and the gate voltage is 4 volts, plot the current versus VDS. In the ohmic region, what I would do is increase VDS from 0 to 6 volts. I know the turn-on voltage is 1. I know K sub n. Here's the equation for the current in the ohmic region. And if you plot it, you get a parabola. The left-hand side is actually correct. As I apply more voltage, I get more and more current. And the slope right here, V equals IR, the slope is 1 over resistance. That's the admittance. As I change VGS, this comes down and the slope changes. So that's your voltage-controlled resistor. This part right here doesn't actually make sense. This says that as I increase the voltage, the current drops. That's actually not the case. What happens is I switch modes. As I increase the voltage, I get more and more current, up until I run out of charge carriers. Once I run out of charge carriers, the current actually stays constant. So actually the correct model would be it's ohmic up until the apogee, then it's a constant. That's where you go into the saturated region. If I put the two together, this is MATLAB code. I'm going to sweep the VGS from 2 volts to 6 volts, and then plot the same curve. When VGS is 1 volt, there is no current flow. I haven't created a channel. At 2 volts, I get more current, 3, 4, 5, 6. In the saturated region, current is related to volt squared. It's VGS minus V turn on squared. And you can see this, the nonlinear spacing, that's the square law. You can also see the ohmic region. As I increase the voltage VDS, I get more current. That's these guys right here. Up until it becomes flat. The transition from ohmic to saturated is a parabola. The equation for that is when VDS, what was that? VDS is greater than VGS minus V turn on, I'm saturated. Example. Suppose I had this curve. This is what the VI characteristics look like for MOSFET. And again, I can see here's the ohmic region, here's the saturated region. Suppose I want to find out, given that data sheet or that graph, what is K sub n? What's the transconductance gain? Well, the trick is pick a point and then throw in the equation. But you got to watch which region I'm in. If I pick point A, I'm in the ohmic region. So here's the equation in the ohmic region. IDS is 2 milliamps. VGS is 7 volts. VDS is 2 volts. The turn-on voltage is 1 volt. Actually, here it's 2 volts. The turn-on voltage is, I know, it's less than 7, 6, 5, 4, 3. I've got current flow at 3 volts, so the turn-on voltage has to be less than 3. If I draw this parabola, where's the tangent? In this case, it's actually at 2 volts. So I know all the parameters in here, plug it in, and I got K sub n is 0.25 milliamps per volt squared. I could also pick a point in the saturated region. In the saturated region, the current is related to volt squared. IDS is 2 milliamps. VDS, I don't care, it's not in the equation. VGS is 6 volts, and again, V turn on is 2 volts. Gives you, again, 0.25 milliamps per volt squared. So it shouldn't really matter which point you pick. Pick a point, throw in the numbers, I should get the same answer. So that's finding the parameters for a MOSFET given the graph. To use the graph, let's look at this problem. Suppose I have this MOSFET circuit and I want to find out what is the operating point, meaning what is VDS, IDS, when the gate voltage is 0 volts, 4 volts, or 6 volts. The way you approach this is you draw the load line. Can we do a lot of load lines in this class? The load line would be, for the MOSFET, here's the graph. The other part of the load line is VDS plus I times R is 6 volts. So when the current is 0, I'm right here at 6 volts. If I short this, I'm at 3 milliamps. So it'll be a straight line going between 3 milliamps and 6 volts. Looks like this. Now, just read off the graph. When VGS is 2 volts, I'm right here on the load line. Current is 0, VDS is 6 volts. When VGS is 4 volts, I'm on this line. Here's where it intersects. So the solution is 5 volts and 0.5 milliamps. When VGS is 6 volts, I'm right here. I'm now in the ohmic region. And it's 2.5 volts and 1.75 milliamps. So that's kind of how MOSFETs work. What we'll look at in our next lecture is how to use a MOSFET as a switch. ECE 320, lecture number 22.